In this video, we'll consider the design of a feed-forward controller for a blending tank, and we'll do this considering the steady-state design equation for the blending tank, and we'll perform our design using only time domain equations. The objective of this operation is to maintain the effluent concentration X at some set point XSP. We'll assume that the composition of incoming stream 1, X1, is a disturbance, that W1 and X2 can be considered constant, and that W2 is our manipulated variable. We can begin by writing steady-state mass and component balances for the level in the tank. At the steady state, the total mass balance says that the flow rate in should equal the flow rate out. And the solute component balance says that the rate at which the solute enters is equal to the rate at which the solute leaves. Here we are using the bars to indicate the steady state values of each of these variables. Now we can use the total mass balance to eliminate W bar from the component balance and solve for W2, the desired flow rate for stream 2. This equation tells us what W2 should be. Now if we let X1 deviate with time, and we want to keep X at its set point, which we'll call XSP, we can do so by manipulating W2, and this equation tells us exactly how. We simply substitute X bar for the set point XSP, and we substitute X1 bar with its time varying value. Now if we know how X1 is changing with time, we know exactly how W2 should also be changed with time. And this is a control law for the feed-forward controller based on steady-state considerations. Now to design the controller, we still need to know how the rest of the control loop behaves. This only tells us what W2 should be. Let's suppose we have a composition sensor transmitter with a signal range of 4 to 20 milliamps and some minimum measurable value X10 and a gain for the sensor transmitter KT. Let's assume further that we have a linear current to pressure transducer and a valve that has negligible dynamics. Then W2 will be the valve gain multiplied by the current to pressure transducer gain multiplied by P minus 4, where P is the signal coming out of the controller, and 4 is the minimum value of that electronic signal in milliamps. And W20 is the flow rate W2 when the valve is all the way closed. Remember, many equal percentage valves, for example, have a non-zero flow rate at zero lift. Now we can design the controller. We begin with our steady-state design law for the process, and we substitute in the W2 flow rate that we got from our valve equation. For the variation in X1 with respect to time, we can solve our sensor transmitter equation for X1 of time and plug that in. Making these substitutions, we can then solve this equation for P, which will appear on the left-hand side after we substitute in for W2. P is the output signal from the controller, and this tells us what P should be as a function of our set point and our measured value for the disturbance X1M. Now, of course, that design for the feed-forward controller makes a lot of assumptions. For example, it's assuming that the valve behaves linearly and that the pressure in the feed line for stream 2 is not changing with time. But valves don't always behave linearly, and the pressure in the feed line might be varying. So frequently, feed-forward control loops like this include a separate flow controller that's designed as a feedback loop. In this design, the feed-forward controller determines what the set point W2 should be for a flow control loop. The flow control loop measures the flow rate W2 and adjusts the valve to eliminate any error in the flow rate W2. This type of design, where a flow controller is included at a control valve, is very common. The design we considered here for the feed-forward controller was based on simple steady-state analysis of the total mass balance and the component balance on the tank. In the next video, we'll consider a dynamic design But rather than doing it in the time domain, we'll do it in the Laplace domain.